Hi, everybody. At the end, oops, come back. Okay, at the end of the last lecture, I left you with a question to think about. I'm sure you've been pondering it since you listened to that lecture. But remember that we were talking about the quantificational properties, quantificational truth, quantificational falsity, quantificational indeterminacy. And I left you with this sentence, which I wanted you to think about how you would establish that it is quantificationally false. And before I do that one, let me just remind you that we said that a sentence is quantificationally true if and only if it's true on all interpretations. It's quantificationally false if and only if it's false on all interpretations. And then the third possibility is the sentence is indeterminate, and that means it's true on at least one interpretation and false on at least one interpretation. Now, since there are an infinite number of possible interpretations, unlike back in sentential logic, there's always a finite number of truth value assignments we can run through. There are an infinite number of interpretations, so we can't run through them all and say, oh, look, this makes it false, that makes it false, this one makes it false, because there are too many of them. So the way in which we establish quantificational truth and quantificational falsity is by giving an argument in the meta-language. The way that we would establish quantificational indeterminacy is by actually constructing one interpretation that makes it true and one interpretation that makes it false. To show that a sentence is not indeterminate, well, then you have to show it's either quantificationally true or quantificationally false. And that would be an argument in the meta-language. Just to kind of finish up this review, if you want to show that a sentence is not quantificationally true, how do you do that? You construct one interpretation on which it's false. Right, so it's just like with ESO. If you wanted to show that a sentence was not truth functionally true, you found one truth value assignment on which it's false. If you want to show that a sentence is not quantificationally false, then you have to construct one interpretation on which it's true. So, all of this is very reminiscent of what we were doing back in truth functional logic. It's just that things are more complex because our notion of interpretation is a more complex notion than the notion of truth value assignment. Okay, let's get back to this one. We want to show that it's quantificationally false. And so we have to give a little argument in the meta-language to establish that. I'm going to do, just to kind of vary things, just to remind you the various ways in which you can prove things, I'm going to prove this by reductio ad absurdum, or what we called an indirect proof. So I'm going to start out by supposing that it's not quantificationally false, okay? And then I'm going to reach a contradiction, and then I'll say, oh, see, it has to be quantificationally false. There can't be a truth value, an interpretation that makes it true. So I'm going to start out by supposing that there is some interpretation that makes the sentence true. Okay? So if it makes the sentence true, then it has to make the main operator of this sentence is the ampersand, right? Then it has to make both of those conjuncts true. So if it were to make the first conjunct true, then something in the universe of discourse of that interpretation that we're supposing exists must be in the extension of F, right? There's something that's F, but it's not in the extension of G, but not in the extension of G, okay? And in order for an interpretation to make the second conjunct true, everything that's in the extension of F has to be in the extension of G. So you're seeing how this is going to reach, we're going to reach a contradiction. I'm going to have to scroll up a little bit. That interpretation must put everything that is in the extension of F also into the extension of G. Right? Because what it says is everything that's F is G. But wait a minute, how could it be the case that there's something that's in the extension of F that's not in the extension of G, but at the same time, everything that's in the extension of F is in the extension of G? So there's our contradiction. This can't be. So by reductio ad absurdum, there cannot be an interpretation that makes the sentence true. Therefore, it is quantificationally false. That's what we mean by quantificationally false. Okay, done. Sorry it's not all on one screen, okay? So that was the problem that I left you with at the end of the last lecture. And, you know, it looks kind of like a long-winded proof, but I wanted to write out all the steps of the proof, which is what we would expect you to do too if asked to do such a problem. Okay, let's just do a few more examples. A lot of the examples that we've done so far have involved two-place predicates rather than one-place predicates. And the two-place predicates, we've been drawing pictures with dots and arrows. What I wanted to do is to give you a sense of how you would approach constructing interpretations when you have one-place predicates rather than two-place predicates. So let's just start with a fairly simple example. There's something that's F and G, and there's something that's F and not G, and there's something that's not F, there's something that's not F, but is G. Okay, so suppose we want an interpretation that makes this true. Okay, if there's an interpretation that makes it true, it has to make all three of these sentences true, right? There's got to be something that's F and G, something that's F and not G, something that's not F and G. And so I'm going to give an abstract interpretation that that does the job. You might be able to think of a natural language one. I'm not going to spend the time trying to, because I've admitted I'm kind of bad at it. But giving an abstract one is really fairly easy. So we need to specify a universe of discourse. We need to specify an extension for F, and we need to specify an extension for G. Okay? So there's got to be something that's both in F and G. So I'm going to have one. I'll put one into the universe of discourse, and I'm also going to put it into the extension of F and the extension of G, so we've taken care of that one. I want something that's in the extension of F, but it's not in the extension of G, so I have to add something else to the universe. I'm going to put it into the extension of F, but I'm going to leave it out of the extension of G, so I've taken care of that one. Now I need to make the third sentence true. There's something that's not in F, but it is in G, so I'm going to have to add something else. I'm going to put, say, 3 into G, and I have to put 3 into the universe, but I'm leaving it out of F. And boom, I'm done, right? So 1 is the guy who is both in F and G, 2 is the guy who's in F but not G, and 3 is the guy who's in G but not F. And that does it. And that was really easy without thinking about, it's just so much easier to construct an abstract interpretation where you can just engineer a world that does the job that you want it to do, rather than looking out into the real world and trying to think of some pocket of the real world that makes this true. Okay, so there's that one. Let's do another that makes it true. Okay, for all x, fx and gx, then hx, and not for all x, fx, then hx, and I need to put a set of parentheses around here because of our syntax, and not for all x, gx, horseshoe, hx. Okay, and we want an interpretation that makes this true, say. Okay, and by getting back to sort of the meta-theoretical stuff, what we've shown up in this problem, when we found an interpretation that makes it true, is that essentially we've shown that it's not quantificationally false, right? Okay, and we'll do the same thing for this sentence. Okay, so we've got 3 sentences. It's a conjunction. The interpretation has to make all 3 of these true. So we need a universe of discourse, we need an extension of f, and we need an extension of g. Okay, so let's see here. The first sentence says, everything that's both f and g is h. Okay. The second sentence says, but not everything that's f is h. And the third sentence says, but not everything that's g is h. Okay, oops, I need an h too. Sorry about that. We have 3 one-place predicates. Okay, and again, I'm giving this when I say f is equals, g is equal, h is equal. I'm saying that the extension of f is whatever set that follows, the extension of g, the extension of h. Okay, so I'm going to approach this in a similar way, right? So we want it to be the case that everything that's both f and g is h. Well, we could just make it so that there's nothing that's both in f and g, and then it would be true in virtue of there not being anything that satisfies the antecedent condition. So let's hold off on the first sentence first and see what we have to do to make the second and third sentences true. We want it to be true that not everything that's f is h. So in other words, there's got to be something that is in f, but we leave it out of h, okay? And 1 is playing that role. It's not the case that everything's f is h, so we've taken care of that by putting 1 into the extension of f and leaving it out of h. Now, how would we make the second sentence true? It's not the case that everything that's in the extension of g is in the extension of h, so let's put 2 into the extension of g, but we're leaving it out of the extension of h, okay? So we've taken care of that one. And now we want it to be the case that everything that is in the extension of both f and g is in the extension of h. Well, this, by the way, we have 2 things here. This actually does this, right? This interpretation, as it is, will do it, because if there isn't anything that's both in f and g, as we have here, then it's true regardless of what's in h, right? Because remember that if there's nothing that satisfies the antecedent condition, the universally quantified conditional is sort of vacuously true. And so that would do it. So we could have, so one possibility would just be have the extension of h be the empty set. Whoops. Right? That would do it. But let's make it so there is something that's in both f and g. So we could have the universe of discourse. I'm just trying to give you options here and strategies. Suppose we put, oops, and we needed the brackets on the other side. Suppose we have, say, 3 things in our universe of discourse, and we put, say, say 2 is in both F and G. Well, then in order to make this sentence, the first sentence, true, everything that's both in F and G has to be in H. So we're going to put it into H. So we've now taken care of the first sentence. How about the second one? It's not the case that everything that's in F is in H. So we need to put something else into F and leave it out of H. And it's not the case that everything that's in G is in H. So why don't I just put 3 into G, and I leave it out of H. I mean, look, there are lots of ways we can do it, but that would do it as well. So, look, I thought I had charged this. I'm having issues with my pencil. Okay, so either one of those interpretations, and well, there are an infinite number of interpretations that could make it true, but those are kind of simple ones, and I wanted to show you how you could do abstract interpretations where you only have one-place predicates, because the extension of a one-place predicate is a set of objects, whereas the examples we had done before, we had two-place predicates, and the extensions of two-place predicates are sets of ordered pairs of objects. Okay, so let me do another one. Before I start talking about the other quantificational properties, which I want to do, let's do an example where we show that a sentence is quantificationally indeterminate. Okay? Let's hope that's enough charge. Okay, so the sentence, let me play my here. Okay. The sentence, let's change color. The sentence we want to look at is this. Whoop, that's not the sentence we want to look at. The sentence we want to look at is this. If everything that's F is G, if all F's are G, then whatever A names is F, but it's not G. Ooh. And so we want to show that this is quantificationally indeterminate. Now remember, to say that a sentence is quantificationally indeterminate is to say that there's at least one truth value, sorry, there's at least one interpretation that makes it true, and there's at least one interpretation that makes it false. If I had said truth value, then it would have been about truth functional indeterminacy. Okay, so what we have to do is to construct two interpretations, one that makes it true and one that makes it false. Let's first do one that makes it true, okay? Now, I gave you this example because this one actually has a constant in it as well. So remember, when you construct an interpretation, you have to specify a non-empty universe of discourse, the meanings for predicates, and in this case the predicates are one-place predicates, and if we do this by extension, we have to figure out what set of objects are in the extension of the predicates. And we also, if there is a constant, which there is here, we have to give a referent for that constant, which means we have to assign to that constant some member of the universe of discourse that it names. Because they're singular terms, they act as names, and they have to name something in the universe of discourse, not outside the universe of discourse. And remember, all of our names refer. They have to have reference. They have to name some object. Okay, so what do we need? We need an interpretation where we specify a universe of discourse, the extension of F, and the extension of G, and we give a referent for the constant A. Okay, let's look at the sentence. How can we make this sentence true? Well, you might think, how could it be true? Because the antecedent says, everything that's F is G, okay. But the consequent says, this guy A, whatever it names, is F but not G. So how could we possibly find an interpretation that makes that true? Well, remember, since the the main operator is the horseshoe, if we find an interpretation that makes this false, then the whole thing is true by falsity of the antecedent. So that looks like it's a good strategy. So why don't we have why don't we put two things into the universe of discourse, and we'll put one of them into F, but we leave it out of G. So 1 is playing the role of falsifying the antecedent. It's our guy who is in the extension of F, but he's not in the extension of G. I'm leaving him out of the extension of G. So we've already verified the whole conditional by falsifying the antecedent, but we don't have a complete interpretation, right? So we have to give an extension for G, and we have to give a referent for A. Well, there are lots of ways we could do this. Why don't we just put 2 into the extension of G and have A named 2? It doesn't really matter, because this whole conditional is going to be true if the antecedent is false, regardless of what the truth value of the consequent is. I happen to have made the consequent, what is the truth value? Oops. What is the truth value of the consequent? It is, A is, it's going to be, it's false, actually. Okay? Okay. So in order to find an interpretation that makes it true, you have to have the insight that the only way you're going to do it is by falsifying the antecedent of that conditional. And now the rest of this is we need to find an interpretation that makes it false, because we're trying to show that it's indeterminate, that it's true on at least one truth value assignment and false on at least one truth value assignment. Now, if an interpretation is going to make this sentence false, since it is a conditional, well, then it has to make the antecedent true and the consequent false. Okay? Oops. Get in there. Okay, so we need a universe of discourse, we need an extension for F, we need an extension for G, and we need a referent for A. Okay, so everything that's F is G. Why don't we put something into the extension of F, and we also put it into the extension of G? Okay, so we've made that true. But now we want that to be false. Of course, there are an infinite number of ways we could do this. I'm just doing this, kind of in the way that strikes me initially, in kind of a simple way. And we want it to be false that whatever A names is F, but not G. Well, we could just have A name 1, right? And now we're done, right? Everything that's F is G, and A names 1, so that's true, but that's false because we put it into the extension of G. So the whole thing is false. Or, we could have put 2 things into the universe of discourse, and into F we'll put 1, into G we'll put both 1 and 2, so that's true, right? Everything that's F is G, 1 is F, it's also G, and we can have A name 1, and now 1 is in the extension of F, but it's also in the extension of G, so that's false, so the whole thing's false. Okay, so either one of those would do it. So by constructing these 2 interpretations, we've shown that this sentence is quantificationally indeterminate. Okay, trying to decide whether I should do some more. I'm going to do a few more harder examples, because I take these to be fairly simple, but I wanted to make sure that you understood how to construct abstract interpretations that for sentences that have just one place predicates rather than 2 place predicates. Okay. There are other quantificational properties that I want to talk about. So let me first talk about the notion of quantificational validity. What do we mean when we say that an argument is quantificationally valid? Well, an argument is quantificationally valid if, so this is a property of arguments. Let me just write out the definition of quantificational validity. And you already know what it is. I'm sure. An argument is quantificationally valid if and only if there is no interpretation, right? Sounds just like the truth functional one, only now we're talking about interpretations. That makes the premises all true and the conclusion false. Okay, so to show that an argument is quantificationally valid, you would have to give an argument in the meta-language, showing that, suppose we had an interpretation that makes the premises all true. Oh, look, it has to make the conclusion true too. So that would be a matter of giving sort of a little meta-theoretical argument. Once we get to the tree method, then we'll have this method to show that an argument is quantificationally valid. But at this point, without the tree method, we have to establish validity by giving a meta-theoretical argument. To show that an argument is not quantificationally valid, what do? If we have some argument in PL that's not quantificationally valid, well, then we just have to construct an interpretation that simultaneously makes the premises true and the conclusion false. So it has to be one interpretation that both makes the premises true and makes the conclusion false. So this is a little bit more complex than just finding an interpretation that makes a sentence true or a sentence false. So let's look at an example. Let's consider this example. There's one premise and a conclusion. And we want to show that this is not quantificationally valid. Well, what do? We have to construct an interpretation that both makes the premise true and the conclusion false. Okay, so that's somewhat more complex. So let's think about what these say. And what I'm going to do, since we've got two place predicates here, is I'm going to draw a picture so I can kind of wrap my mind around this. And the picture is going to suggest an interpretation that does the job. First of all, I'm already telling you that it's not quantificationally valid. We don't have to figure that out. Okay, what does the first thing say? The premise say? It says everything in the universe is such that there's something it bears G to. So everything in the universe bears G to something in the universe. And I'm just starting out with 3 dots. When we get into more complex problems, we'll start to see how to decide how many things to put in your universe. Sometimes you might need just one thing. Sometimes you might need 2 things or 3 things. You might need 4 things. And that's just a matter of playing around with it and seeing what does the job. Okay, whoops. Okay, that whoops was because the cat knocked my notes off. Okay, so everything in the premise says everything in the universe bears G to at least one thing in the universe. And in terms of dots and arrows, everything in the universe, every dot has an arrow going out of it. So let's see what happens if we have a G'ing go round. So now every dot has an arrow going out of it, and so this is true, right? And what does the conclusion say? It says there's X and Y that are in a non-reciprocal G'ing relationship, right? Where one G's the other, but the other doesn't G the one, right? There's an X and there's a Y. X G's Y. Oh, sorry. That's how do you make it false. Let me back up. To make it true, what it says is there's X and Y who are in a reciprocal G'ing relationship. So there's X and Y such that X G's Y and Y G's him right back, right? So this makes the premise true. To make the conclusion true, we could have two things in our universe and they G each other. So this makes the conclusion true, right? Or you could even have one thing that G's itself and the conclusion is true. Okay, so, but you get the idea that you've got to have kind of a double arrow going between things in order for the conclusion to be true. But we want the conclusion to be false. That's why I was jumping ahead one step in my head initially. We want the conclusion to be false. So we want there to be things in the universe that are in a non-reciprocal G'ing relationship, right? Where it's there's an unrequited G'er. And the picture that I drew of the dots and arrows that makes the premise true actually makes the conclusion false, because each one of these guys is in a non-reciprocal G'ing relationship, right? This guy, let me switch colors so that I don't have to make these bigger. This guy G's that guy, but he's not G'd back by him, right? And this guy G's that guy, but he's not G'd back by him. And then this guy G's that guy, but he's not G'd back by him. So it's like overkill. There are lots of things that are in non-G'ing. All three of the things are in non-G'ing relationships. So this picture actually makes both the premise true and it makes the conclusion false. So we've got it. This is a picture of a world where, sure enough, the premise is true and the conclusion is false. It's not an interpretation. It's just kind of wrapping our minds around what an interpretation would have to do in order to verify the premise and falsify the conclusion. But from this picture, we can easily construct an interpretation. We think of that as 1, 2, and 3. It suggests an interpretation. So there's kind of a canonical way of constructing an interpretation from these pictures. It suggests an interpretation that's got 3 things in it, right? And what are we going to put into the extension of G? Well, we just kind of read it off from the picture. We have 1 bears G to 2, 2 bears G to 3, and 3 bears it back to 1. So sure enough, everything in the universe bears G to something in the universe, right? So everything in the universe shows up as the first member of an ordered pair. But we've left out that we didn't put in 2, 1, we didn't put in 3, 2, and we didn't put in 1, 3. So the conclusion is false, right? It's not the case that there's X and Y that G each other. And so this does the job of showing that the argument is not quantificationally valid. Okay, so that's quantificational validity. Let's do another one before I move on to quantificational equivalence. I just want to make sure that you understand what these concepts are. It's all pretty much the same in terms of showing that an argument is not quantificationally valid, showing that 2 sentences are not equivalent, which we'll get to in a minute. You just have to have a sense of, can I do this by constructing an interpretation? Or do I have to give an argument in the meta language? And you already know how to think about these things because they're so similar to what we were doing back in truth functional logic. But of course, the whole thing's richer because we have a richer language that we're dealing with. So let's take a look at another nice example. Let me see. Okay, let's look at another argument and think about the validity. Okay, this is, do I want to do one this complex? Sure. Sure. Again, it's an argument with one premise, albeit a complicated premise. Oof, conclusion. I may regret doing this one at this point, but we'll do it anyway. I think you're ready for this. Wow. So we want to show that this is not, I'm telling you, this is not quantificationally valid. I'm already kind of regretting writing this down, but that's okay. Here we are. Okay, so we need to find an interpretation that makes the premise true and the conclusion false. Okay, the premise is a conjunction. So the interpretation has to make both of those conjuncts true. And the conclusion is a universally quantified conditional. We'll get to that after we do the think about the premise. Okay, so I'm going to draw a picture, once again, that's got 3 dots in it. Just 3 is a nice small number. Okay, let's think about what the first conjunct of the premise says. There's something such that given anything at all, it's not the case that that thing G's the anything. So in other words, there's something that fails to G everything, right? Something G's nothing, or fails to G everything. That's what the first one says. Okay, done. we already have that. If there's no G'ing going on in this picture of the 3 dots, there's already something that doesn't G anything, namely everything. Right? Okay. But let's look now at the second conjunct. There's something that G's everything. Does that look like everything? No, of course it doesn't. Something G's everything. Okay, so we need to have a universal G'er. You know, so what I'm doing in this problem is I'm really putting together all the stuff that we've done, you know, back in chapter 7 and now in chapter 8. And, okay, so we have to have a universal G'er. And why don't we have that guy be the guy on the top? So he G's that guy, he G's that guy, but he also G's himself. Okay, so that's true. And still, is there something that doesn't G anybody? Yeah, both of these guys don't have any arrows coming out of them. So both of them make the first conjunct true. Okay. Now, so this little picture here makes the premise true. All right, now let's take a look at the conclusion. What does that say? Everything in the universe is such that if that's true of it, then that's true of it. And what does that say? Everything in the universe is such that if there's something it G's, all G'ers, that is right, if there's something that it G's, if it's got an arrow coming out of it, then it G's everything. So basically it says all G-ers are universal G-ers. Do you understand what I mean by G-ers? You know, it's got an arrow coming out of it. So everything that has a dot coming out of it, everything, or has an arrow coming out of it, has an arrow pointing to everything. Right? Because, again, everything is such that, everything in the universe is such that if there's something it bears G to, then it bears G to everything. So if it bears G to something, it bears G to everything. Well, the picture that we've got here actually makes the conclusion true, because this is our only G-er. He's the only guy who's got an arrow coming out, and he actually G's everybody in order to make this, the second conjunct of the premise, true. Okay? So we need to change this so that there's somebody who falsifies the conclusion. There's got to be somebody in the universe who G's somebody but not everybody. Okay? So why don't we have this guy here? Why don't we have him G the guy to his left? And so he, the red dot, falsifies the conclusion. Okay? The red dot falsifies the conclusion. Because he G's somebody, namely the guy to his left, but he does not G everybody. Okay. Let's just make sure that we haven't disturbed the truth of the premise. So remember, we also had to have it be the case that something doesn't G anybody at all. That's this guy. Okay, so the green dot verifies the first conjunct of the premise. He's our guy who doesn't G anybody, right? So something doesn't G anybody at all. Let's make him blue. The blue dot, okay, so we have the blue dot verifies the second conjunct. He's our universal G-er. And then our red dot, okay, so let's see, the red dot falsifies that, and the green dot, verifies that. And so this picture, this colorful picture, this colorful world, is a world in which the premise is true and the conclusion is false. What I was trying to say is that both conjuncts of the premise are true and the conclusion is false. It actually wasn't that complex, but it's an interesting problem, and it shows how you can play around with these pictures and come up with interpretations that do, a bunch of things at one time. Now, I don't have an interpretation yet. I'm going to construct the interpretation from the picture that I've drawn. But I'm thinking, boy, I think it would be pretty tricky to come up with a natural language interpretation that did this. But some of you might be good at that. I don't know. But let's take a look at the picture and see what interpretation it is suggesting to us. If we think of that as 1, 2, and 3, well, we're putting 3 things into our universe. And what's going on? Who's G'ing whom? Okay, well, 1 is our universal G-er, right? verifying the second conjunct of the premise. He G's 1, whoops, I don't need that comma. He G's 2, and he G's 3. Okay. And now 2 is our guy who G's somebody, namely 3, but he doesn't G, we left out 2, 1, 2, 2, so he doesn't G everybody. And 3 never shows up as the first member of an ordered pair, so he's the guy who verifies the first conjunct of the premise. And so that is an interpretation that shows that the argument is not quantificationally valid. That was kind of fun. Okay, so now I'm trying to decide whether I should talk about, there are 2 other properties, or 3 other properties that we haven't talked about. There is quantificational consistency, quantificational equivalence, and quantificational entailment. You know what these mean already without my telling you. So let me just, while I'm charging the pencil a little bit more, let me remind you what they mean. Consistency is a property of sets, right? So to say that a set is quantificationally consistent is to say that there is at least one interpretation that simultaneously makes all members of the set true. So to show that a set is quantificationally consistent, you construct an interpretation that makes each set member true, okay? That simultaneously makes each set member true. So keep in mind that this is a property of sets. Quantificational equivalence, what does that mean? Again, you know what this means because you're just supplanting the notion of truth value assignment with the notion of interpretation. 2 sentences are quantificationally equivalent if and only if there's no interpretation on which they differ in truth value. So every interpretation will either make them both true or make them both false. They have the same truth value on all interpretations. So equivalence is something that holds or does not hold between pairs of sentences. And quantificational entailment, well, you remember the quantificational entailment was essentially a close cousin to quantificational validity. We talked about it's something that holds between a set of sentences and a sentence. We say that a set of sentences quantificationally entails a sentence if and only if there's no interpretation that makes the members of the set true and the sentence false. Okay, so you know what these things mean already. I may not do examples of all of them in this lecture, but I think that you know you could do some practice problems doing them. I think that I want to do just a couple more examples. I know you might think, no, don't do any more. That are more interesting, like the one that we just did. Okay. So make sure that you understand what these definitions mean and what you do to establish consistency and to establish inconsistency. To establish inconsistency, you would have to show that no interpretation could possibly make them all the members of the set true. That would involve a little meta-theoretical argument. To show that 2 sentences are equivalent, again, you'd need a meta-theoretical argument. To show that they're not equivalent, you would need one interpretation that makes them one true and one false. Okay? I just want to do, here's a nice example because it involves, again, trying to parse a sentence that somewhat more syntactically complex. Okay. Let's think about this sentence. And suppose I don't tell you what the quantificational status of the sentence is, and we want to try to figure out what the quantificational status of the sentence is, and then establish that we're right, okay? All right. What is the main operator of this sentence? It's this universal quantifier. It, again, is a universally quantified conditional. It's an A-ish kind of sentence, right? It says everything that has this property has that property. Okay, so let's think about what those two properties are. Let's look at them in turn. For all y, h, x, y. This just says that x bears h, or h's, everything, right? And what does the thing in the consequence say? Something bears h to x. Okay, so the whole thing becomes, for all x, put this aside for a minute, for all x, if x bears h, if x bears h to everything, then something bears h to x. If x bears h to everything, then something bears h to x. Okay, well, let's just try to wrap our minds around this by drawing a little picture. And that might give us some insight as to into the quantificational status of the sentence. Everything is such that if it bears h to everything, so let's have this guy bear h to everything, then something bears h to it. Oh, wait a minute. If this guy bears h to everything, well, he's got to bear h to himself. So indeed, something does bear h to him, namely himself. Ah, wait a minute. How could this possibly be false in interpretation? Because if you have something that satisfies the antecedent condition, it's got to satisfy the, anything that satisfies the antecedent condition has to satisfy the consequent condition. Because if you've got something that's a universal h'er, that h is everything, well, it's got to be h'd. Something's got to bear h to it, namely itself, because it h's everything, including itself. Ah, my insight is this is quantificationally true. There couldn't be an interpretation that makes it false. Now, this little picture just happens to be, one little world, right? In order to establish that it's quantificationally true, I need to construct an argument in the meta-language. So that's what I'm going to do, but I kind of know exactly how that argument's going to go because I just went through it here when I drew this picture. So here's how I would argue. This is quantificationally true because if everything or if everything, okay, how am I going to put this? It seems kind of obvious. I'm trying to figure out how to express it. Suppose something in the UD bears h to everything. Right? We're talking about this with respect to an interpretation. Something. Okay, so I want to make sure that when you construct these arguments, you make reference to interpretation. So consider an interpretation in which something in the UD bears h to everything in the universe. well, then that object must bear H to itself, so something bears H to it, namely itself. So any object in the UD that satisfies, perhaps I'm saying more here than necessary, but I want to make sure that it's really clear, that satisfies the antecedent condition must satisfy the consequent condition. Okay, so there can't be an interpretation that makes it false. Every interpretation makes it true. Okay, I think I'm going to stop here. I think that'll be the last example I do. I just want to make some general remarks and then talk about what I take you to be responsible for on the quiz this week. Okay. When you want to establish that a sentence is quantificationally true, or a sentence is quantificationally false, or that an argument is quantificationally valid, or that two sentences are quantificationally equivalent, these are all tasks that will involve constructing a little meta-theoretical argument, right? Because there are an infinite number of interpretations. Make sure that you sort of invoke the definition of the concept in question. To show that a sentence is quantificationally true, you've got to show that it's true on all interpretations, or that there could not be an interpretation that makes it false. To show that an argument is quantificationally valid, you need to show that any interpretation that makes the premises true must make the conclusion true. So just as when we were doing these meta-theoretical arguments back in truth-functional logic, you always had to make reference to truth-value assignments and invoke the meaning of the concept under discussion. Similarly, here you have to invoke the notion of interpretation and make reference to the definition of the relevant quantificational property. Other problems that you might do will involve constructing interpretations rather than giving arguments. So if you want to show that a sentence is indeterminate, you must give two interpretations, one that makes it true, one that makes it false. This is actually constructing interpretations, where you give a universe of discourse, meanings for predicates, reference for constants if there are constants. If you want to show that an argument is not quantificationally valid, you must give an interpretation that makes the premises true and the conclusion false. If you want to show that an argument is quantificationally consistent, we haven't done an example of this, but you can do this, you just give one interpretation that makes each member of the set true. So have in mind, have a good grip on what you need to do in order to establish whatever it is that you're being asked to establish. So that's the kind of stuff that's going to be on this quiz. How about I don't do anything involving entailment, because I didn't mention we didn't do an example with entailment, but there might be things involving quantificational status of sentences. There might be something involving validity or invalidity of an argument. And there might be something involving equivalence, even though I haven't done an example, but I think you know how to do that. Okay, so let me end here. Tomorrow is a university holiday, but as I said in the note that I wrote to the class, I'll have an office hour at 2 anyway, in case somebody wants to ask questions. Okay, bye for now. Hope everybody's doing well.